the tutorial yesterday, we're not going to go through the whole story again, but we had this scattering theory description. And the bottom line is a modeling equation. The way to generate the actual wave field that the Earth experiences in a perturbative sense, and it depends on everything we're used to modeling requiring. Number one, what model type are you interested in modeling? And every detail of the medium properties are required to generate the wave field. So that's not a surprise. It's very comforting. At least it's something we say here that's consistent with what the rest of the world believes. Okay? Let's say you are committed to the program that to do things in processing, you started with a modeling idea and you model match. Let's say you wanted to remove multiples by model matching. So there you go. There's that G in your phone collects primaries and will be primaries and multiples predicted, and to predict the multiples from modeling would require number one, model type. Which model type is elastic, anisotropic, what form of anisotropy? Heterogeneous, what are all the properties? If you cannot specify that, you cannot model predict the multiples. Clear all of that in detail. Any error in that will make an error in the multiple prediction through modeling. You come up with a direct inverse procedure, this set of equations, and you get a simple example of it being this machine on the bottom for free surface multiple, and you have a series which eliminates every free surface multiple or requires the wavelet. It doesn't know where the water bottom is, it doesn't care what kind of earth it is. That algorithm does not change. If the earth is acoustic, elastic, anisotropic, all it cares about is that when you send a wavelet in, a wavelet times what an impulse would be comes back, the convolutional model. So the difference between what a direct inverse communicates and what modeling communicates is very clear and transparent here. So there's a part of our community that is fully committed for all things to model matching and updating as a way to do inverse. There are times when a forward model run in an inverse sense is equivalent to a direct inverse. There are times when, I'll repeat that, a modeling run in an inverse sense is equivalent to a direct inverse. The time is, the circumstance is when the direct inverse is linear. For example, depth with knowing the velocity. That's a direct inverse. If you know the velocity, you will get the depth unambiguously. You know search, you do an integral, and you get a depth. Yes, that's a direct inverse, which is linear in the data. That procedure is equivalent to a forward modeling run backwards. It's only when the direct inverse is linear that it's equivalent to a forward problem run in an inverse sense. Okay? As soon as you have a nonlinear problem, so we can illustrate this, there's a paper we've written on this called The Antidote to Indirect Methods and FWI. That's going to be published in the special issue of TLE on FWI, coming out in September, because there's such a huge commitment, financial and otherwise, to the current view of way of doing FWI. I think it's not sort of some little thing done in the corner. It's worth, if you have that level of commitment, to raise fundamental issues about what we're doing. So, in other words, for example, if you have a formula S equals AR, and this is a forward problem, and that's the inverse would be S over A. You had some inverse of it. So the inverse is linear, and you can say, well, it's the same as taking the forward problem and solve it for R. It's that simple. But let's say you had a nonlinear problem, which was S equals AR plus and so on. And you decided that you know it's nonlinear, so this equation is AR, we happen to know, over 1 minus R. And we know that there is one unique, exact solution for R. You solve for it. We showed that yesterday. It was something that R is S over A over 1 plus S over A. You give me S, you give me A, there is one R, real unique number. Let's say you take this formula and you say, well, I'm gonna, I know it's nonlinear, but you didn't know this, yes? You didn't happen to know this, which allows you to go in the other direction. So you took a quadratic estimate of the forward. Solve that in the inverse, you get two roots. They can be complex. See how different right away. Then as soon as nonlinear, this goes one way, the other way. You understand? This is a quadratic equation. Minus b plus or minus s. So that's a hint of the difference. So what is, to a person who you meet in the elevator on the street and they say, well, what is all this, why is this so different? The reason is when you do modeling, you actually have to create the primary multiple. You have a medium, and the method is building through construction of what a wave does, making the primary multiple. The inverse is entirely different. You don't have to make primaries and multiples, they're recorded. All you're doing is separate them. That's a totally different activity than making them through their experience. So there are lessons on this, about this. Now I'm not going to go through all this, but to the algorithm for free surface multiple, again, giving some context to where we've been yesterday and where we're going today. This is Paulo Carvalho's, from his thesis, free surface multiple removal of every order, or d sub n gives you the order. So you put a 2 there, and it's first order, and so on. Okay? That equation says, if you give me the wavelet, remove it, you do source and receiver deghosting, then that equation tells you is an elimination of every order of free surface multiple. In other words, it predicts the precise time and amplitude of every free surface multiple and never touches a primary. Okay? That's so. First of all, there were other methods for free surface multiple at the time of Carvalho, mainly from Delft. Error for sure, Hunsberg, and they had a different approach. It did not come from the inverse series, and it boiled down to a different method, a method where there was no Q, there was no obliquity factor. This factor was missing, and some felt they were compensating it somehow by doing receiver deghosting, but not source deghosting. There was a whole story about that. And in practice, what that led to was error, offset error, that was increased with offset. And in practice, people then said, we'll do SRME, and to deal with that residual offset error, we'll do radon. Okay, that became the industry standard. Okay? That's what SRME meant. That has a downside that the radon can injure primaries. Radon doesn't commit to. So this won't. So this is more expensive. If you drop the obliquity, this is cheaper. It becomes something you can do in X omega, is the point. If you keep the Q, you have to compute this, and it's more expensive. The point is, if you're committed to both pre-stack and post-stack removal of multiples, in other words, a lot of times when we were using the Delft procedure, the multiple would look like it's coming out in the pre-stack. And then we would stack it, the multiple looked like it came back, because the long offset part would stack in. With the Carvalho, the big news at ARCO when that came back from Brazil was it had no multiple pre or post. There was nothing to stack. At every offset it came out. So if you say, should we spend the extra money? I would say we didn't go from 2D to 3D processing to save money on processing or acquisition. We did not go from 2D to 3D to save money on processing or acquisition. We made that change to get more effectiveness, and at the end of the day, to reduce drilling dry holes. Within that same thinking, you might consider this within that toolbox idea. It's a toolbox issue. Okay? In other words, if you have an isolated multiple and you don't think radon is going to injure some proximal primary, then I would suggest doing that. So we're giving a talk this year at the SCG, been invited to give an overview of multiples for the recent advances brought ahead, and our advocacy is, as it always has been, toolbox. Pick the tool that's appropriate for your, the methods that we provide are not what we will ever view are the choice in all circumstances. Not what we provide is not the choice in every circumstance. It depends on your objective. If you have a structural objective versus a stratigraphic, there are different compromises for the first over the second, and sometimes if you have a, okay? You don't want to touch primaries at any offset if you have a stratigraphic objective. So, but I thought to mention that. That's, so in principle, that's complete. However, as I said, it needs deghosting and it needs a wavelet, and it assumes the source is point. If the source is not a point, either your source is an array and or the receiver is an array, Jinlong showed you how you adjust, okay, this for that purpose. Again, to get that kind of ability to surgically remove the free surface multiple. And he showed that in the case of an interfering primary multiple, because that's the whole objective. Okay? So for the Araujo and Company internal multiple algorithm, expensive, no subsurface information. This algorithm and the previous one, Cavallo's algorithm, are so starkly different than modeling. This algorithm and the previous one, in a paper in 2003 with Bob Stoll, Cavallo, Araujo, and several others, we proved that this and the previous are model type independent. Math proof that those subseries of the inverse scattering series, Ian is an author, yes, are independent of Earth model types. That's an astounding, it's not only independent of subsurface information, it does not care what Earth model type you have in your mind. In other words, if you take that Cavallo or some approximate of that from Delft, and if you, some person starts to do different kind of imaging, anisotropic imaging, and they're worrying, are their free surface multiple codes needing to change because of their Earth model type for imaging? The answer is those free surface and internal multiple codes do not change one line of code. You know, when you change your mind about the Earth model type that you're going to do other things about. Clear? That's astounding, yes.
So this is about anisotropy, but not about anelastic attenuation.
For anelastic as well.
As well?
As well. Yes. There are examples. When we were down in Brazil, Chivani was there, a professor when I was there. He had a modeling code that allows absorption. Araujo produced the data with absorption, put it in Cavallo's code. No, not an ounce of issue with free surface multiple removal or internal. Now, when you get to this, it's an attenuator. So then, what do you mean difference between attenuate and eliminate? Issues start to come. But it's always the leading order attenuator, independent of Earth model type. The different Earth model types, that distinction matters, including
in terms
that.
of effectiveness.
Right, in terms of its ability to predict the amplitude. Yes. The time will not be affected by anelastic. But that's an excellent question. But for me, that's astounding. That because the whole inverse series the entire inverse series is not model type independent. The inverse series is saying, I'm going to determine the Earth properties. The first thing it says is which properties. Okay? So its overall purpose is very model type specific, and different things have to happen when you say different Earth model type. If you say I want inelastic and so on, it puts a factor of Q that it seeks to determine. But there are certain subseries that float independent of that detail. They don't care what the perturbation operator is depending on, what parameters. They behave at a strata that's independent of the relationship between the perturbation operator and what are the parameters within it. Okay? They don't care. Okay? So that's a big step up, and again, a huge difference between modeling. You cannot even imagine, I can, model matching independent of the model type. You understand? So I'm going to model match something, and this model generate. Okay?
All right.
Yes.
Does those equations handle mode conversions at each bounce?
Yes. So there's a paper by Richard Coates and myself, 1994, showing that this algorithm can deal with Richard Coates, a colleague of Clement, can predict the precise time of every first order internal multiple. What that means is every internal multiple that's had a single downward reflection anywhere, all at once, from all reflectors at once, and it doesn't care whether it's P, P, S, P, okay? It can be any combination. That was astounding. Further, this is working with water speed. In water, there is no shear wave, yet it's able to predict the precise time and approximate amplitude of P, P, S, P, for example, yes? That, if you need an example that further speaks to the issue of the difference between model matching and a direct inverse machine, if you model match this in water, you will not be able to generate a shear wave. PPS doesn't exist in water. So you see how different the thinking is. But that's an excellent question. 1994, Coates and Weglein. A last example of this.
How do you spell the codes?
C-O-A-T-E-S, Richard T. Coates.
Yep.
Good man. We were together in Schlumberger, Cambridge. Okay, so this is a leading, so why isn't this an eliminator? Yes? I frankly was after an internal multiple eliminator. I told Araujo, first Cavallo said we don't need Araujo. I'll do free surface and internal. And then when we started looking at the internal, he said, give it to her. It's okay, I'm kind of busy. So, and at some point, Cavallo didn't think it was solvable. It was that tough. Because I was hell-bent on an internal multiple eliminator. I said, it's a W, go do that, and we got the free surface eliminator. We don't have, the W is an attenuator. Why? Because it has no, for the free surface, it has information. It's told that's -1 and where it is. This has no information. Nothing, no water bottom, nothing, no reflection, nothing. So it has to work harder. Its first step into that process of removing an internal is an attenuator, okay, because of that issue. If you, at some point, take this guy and say, I'm making you the water bottom, yes? Then it becomes an eliminator, okay? It becomes like a free surface, but you better have that information. You understand? And at some point, you lose that ability. You don't want to be modeling top salt and so on, base salt, and all the rest. Okay, so I just wanted to point out those. So the prerequisites, when you saw why are we spending all that time on Greenstein prerequisites, is the following. when the prerequisites are better satisfied, the better they are satisfied, the better Carvalho and Araujo work. It never is when the better they work, the worse this works. That's why we have a concern with energy minimization criteria for adaptive. You can have a spectacular norm, you know, LP, yes, that is based on energy minimization. You can better and better satisfy that criteria. There is no guarantee that this and that other algorithm are going to benefit from it. You have intersecting events, yes? You understand? That's why we need a replacement. We need a criteria that's aligned with the algorithm. That the better the adaptive criteria is satisfied, the better the algorithm works. Last year, we proposed one for the free surface, free surface case. Okay? You understand? Something which, as that criteria, so what do? You look at the algorithm itself and look for a quality that it satisfies. Some property of the algorithm that when it's working based on the algorithm, okay? So that quality makes the algorithm, it's aligned with the algorithm's purpose. Never is misaligned. The energy minimization is often aligned, but it's not always aligned. In the past, when it was introduced, it was needed. If we didn't have energy minimization at the time that Eric and Hoos and Carvalho and I did it, the free surface multiple method would have never been accepted. That issue, that need for doing something beyond prediction was essential then. However, that reasonable assumption of energy minimization then is now the biggest obstacle to further progress. That's Yi Lo, Saudi Aramco. It's his biggest issue. He needs to replace it. In his case, everything's interfering. That doesn't work. Okay? So, yes, today's assumption reasonable. Tomorrow is going to be the obstacle, guaranteed for further progress. It's the nature of things. Yes. So we're not casting aspersions. Yes. We were involved with energy minimization. Yes. Everybody understands? So I'm not going to go through. So let me just say one for. So this is an attenuator. It's some leading order. When the words you're going to hear this afternoon over and over are, this is the leading order term towards the elimination of first order multiples. The key words I just said are leading order. Okay? Leading order, first order, we know what that means. One down reflection anywhere. Leading order means it's something but not everything. What is it leaving out? The things that it's leaving out are the things that are going to be addressed this afternoon. Okay? Two things. One is make it an eliminate. Yes. Find other terms in the series. We don't do patch. In other words, the series says it can do everything. This term says I'm not everything. I'm a term. The series says I'm going to do everything. Go find where the rest of the promise resides. Yes, and extract it. So there's activity mining the series to change this into an eliminator. You'll see work on that. There's another issue that we were unaware of, to be frank, that Yi Lo pointed out. Very upset one day, sent us something with so little that I couldn't understand his email. Very upset. When you put, you see, a primary, which is in our mind, it builds, if this is deeper, shallower, deeper, it does the job. But B1 is some form of water speed Stoke FK migration. B1 is not primary, it's your data. If you knew what primary was to begin with, you wouldn't have a problem. Okay. It's the data. Okay. Now this machine was designed for, within the data, the primaries dealing with each other. But the data has internal multiples here. And those internal multiples will be, at times, for 3 and more generators, reflectors, beyond what this leading order can accommodate. It's issues. What do I mean by issues? It will do the worst thing imaginable. It will produce false events. They're not primaries. Okay? They're not multiples. They're something completely not in your data. called spurious events, you'll hear people say. So, in other words, when there are internal multiples in here, if you have two generators, Haiyan Zhang and Simon Shaw, that will never happen. You'll never get with two. They published a paper a few years ago, okay? For two reflectors. Now, you get more than two, which you're already in salt. Water bottom, top salt, you get one more reflector, yes? You're in three, then the spurious event can arise. The series doesn't have a problem with it. There are other terms that remove it. In fact, if you look at the series, there are others that are doing the negative of that problem. So there's an activity here. Hung and Chow will be talking in a minute about seeing that issue, and they're addressing it, removing it. So if that is an issue that you think you have, and they'll tell you when you should expect that to be significant, yes? When you should see it in your data and expect it, and then they will give you the opportunity for a new algorithm to deal with it, which captures higher order terms, leading order, higher order. Certain higher order, there are other people here, Zhao and Wilbert Herrera, who are going to be talking about capturing terms to turn that into an eliminator, yes? So that's basically what we're talking about, okay? How to deal with the limitations of what leading order means. The strength of leading order, and I'll end with that, is every single first order internal multiple, no matter what its history, is predicted with a precise time and approximate amplitude. That's its strength. Its limitation is it's not an eliminator, and it can produce spurious events. Both of those you'll see the response to today. Okay, that's the beginning of this morning's session. Okay, so maybe we could switch to Chow's presentation.